Everybody had a great 4th of July. This is Keith Wiggins with PAG Waste Management. We're back talking about the Handbook of Biomass Downdraft Gasifier Engine Systems. We're in middle of Chapter 5. We're talking about the Ember Downdraft Gasifier. We'll just go back over this section a little bit and pick up where we left off. The nozzle and constricted hearth downdraft gasifier shown in Figure 5, 4.5 and 5.4 and 5.5 is sometimes called the Imbert gasifier, after its entrepreneurial inventor, Jacques Imbert, although it was produced by dozens of companies under other names during World War II. Approximately 1 million of these gasifiers were mass produced during World War II at a cost of about $1,000 US. So, like I made that joke earlier, but whatever. It's important to realize that the cost of producing such a unit today would depend primarily on the degree to which it could be mass produced, since none of the components are inherently expensive. Air gasifiers can be operated either by forcing air through the funnel, pressurized, or by drawing the air through the fuel suction. In practice, gasifiers that fuel engines generally use the suction of the engine to move air through the gasifier and clean up train. These are called suction gasifiers. We will describe only suction gasifiers here, although only minor modifications are required to build pressurized gasifiers in Chapter 8. A large number of descriptive articles on gasifiers appeared during World War II, but no detailed drawings have been located from that period. Fortunately, formulas for determining critical dimensions are given in a number of older references. Renewed interest in biomass gasification has manifested itself in the fact that a number of individuals and groups have built modern versions of the Imbert gasifier. Plans and manuals for constructing some of these designs are available from several groups, and they're shown there. Some of these gasifiers have been attached to cars and trucks that have succeeded in traversing the country on several occasions. In particular, Mother Earth News and its subsidiary Experimental Vehicle News have performed extensive tests on gasifiers and have produced and published informative articles and plans with photographs of fabrication steps. The plans are sufficiently detailed so that a skilled welder can fabricate a gasifier for relatively small expense. In 1978, a number of tests were performed under a CRI contract on a 75 horsepower Heiselman Imbert type downdraft gasifier. The gasifier was built in Sweden at the end of World War II and was imported into the country by Professor Bale at the University of West Virginia. Professor Bale used the gasifier in tests during which the gasifier operated on wood pellets, and oxygen. Subsequently, the gasifier was sent to SERI in Colorado for further testing with a 15 kilowatt Onan electric generator. More recently, the gasifier has been used to gasify peat by Professor Goldhammer at Lowell University. The gasifier is now being used by Syngas Systems Inc. to generate producer gas to test gas cleanup systems for use with its 750 kilowatt power generator. Although much of the testing was qualitative in nature, the authors have had considerable experience in running this interesting technological antique. So, next section is a description of downdraft Imbert gasifiers. So in figures 5.1 and 5.2, the upper cylindrical part of the inner chamber is simply a magazine for the wood chips or other biomass fuel. During operation, this chamber is filled every few hours as required. The spring-loaded cover is opened to charge the gasifier, and then is closed during the gasifier operation. The spring permits the cover to pop open to relieve pressure in the case of a gas explosion, thus functioning as a safety valve. About 1/3 of the way up from the bottom, there is a set of radially directed air nozzles that permit air to be drawn into the chips as they move down to be gasified. Typically, there are an odd number of nozzles so that the hot gases from one nozzle do not impinge on the opposite nozzle. The nozzles are attached to a distribution manifold that in turn attaches to an outer surface of the inner can. This manifold is connected through the outer can to a large air entry port. One air nozzle is in line with the port, allowing the operator to ignite the charcoal through this nozzle. During operation, the incoming air burns and pyrolyzes some of the wood, most of the tars and oils, and some of the charcoal that fills the gasifier below the nozzles. Most of the mass of the biomass is converted to gas within the flaming combustion zone, since biomass contains more than 80% volatile matter. The gasifier is in many ways self-adjusting. If there is insufficient charcoal at the air nozzles, more wood is burned and pyrolyzed to make more charcoal. If too much char forms during the high load conditions, then the char levels rise above the nozzle so that the incoming air burns the char to reduce the char level. Thus, the reaction zone is maintained at the nozzles. Below the air nozzle line lies the gas reduction zone, usually consisting of classical in-bare hearth, or in later years, the V hearth. Most recently, the flat plate hearth constriction has been introduced. The latter two hearth designs, V and the hard plate, and the flat plate, the latter two hearth designs accumulate a layer of retained ash to form a high-quality, self-repairing insulation. Improved insulation in the hearth results in lower tar production and higher efficiency over a wider range of operating conditions. After the combustion, or pyrolysis of wood and hot char at the nozzle level, the resulting hot combustion gases, carbon dioxide and H2O, pass into a hot char where they're partially reduced to the fuel gases, carbon monoxide and hydrogen. This procedure results in marked cooling of the gas as sensible gas heat is converted into chemical energy. This removes most of the charcoal and improves the quality of the gas. Eventually, the charcoal is dissolved by these gases and disintegrates into smaller chunks and fine powder that is either swept out of the gases to the cyclone separator or falls through the grate. Tars that have escaped combustion at the nozzle may crack further in the hot char, although tar cracking is now thought to occur above 850 degrees centigrade. The spaces between the nozzles allow some unpyrolized biomass to pass through the hearth construction and then causes all gases to pass through the hot zone at the constriction, thus giving maximum mixing and minimum heat loss. The highest temperatures are reached in this section, so hearth constriction should be replaceable. If tarry gas is produced from this type of gasifier, common practice is to reduce the hearth constriction area until a low tar gas is produced. However, one should remember that hearth dimensions also play a role in the gas production rate. The fine char ash dust can eventually clog the charcoal bed and will reduce the gas flow unless the dust is removed. The charcoal is supported by a movable grate, which can be shaken at intervals. Ash builds up below the grate and can be removed during the cleaning operations. Usually, wood contains less than 1% ash. However, as the charcoal is consumed, it eventually collapses to form a powdered char ash that may represent 2 to 10% of the total biomass, in turn containing 10 to 50% ash. Ash contents depend on the char content of the wood and the degree of agitation. The greater the degree of char reduction, the smaller the resulting particles and the higher the ash, as shown in Figure 3.3. The downdraft gasifier startup and response time is immediate between the fast cross-draft gasifier and the slow updraft gasifier. The in-bare gasifier requires low moisture, 20 to less than 20% moisture, and uniformly blocky fuel in order to allow easy gravity feeding through the constricted hearth. Twigs, sticks, and bark shreds must be completely removed. The reduction in the areas at the hearth and the protruding nozzles present hazards at which the passage of fuel can be restricted, thus causing bridging and channeling, followed by high tar output as unpyrolized biomass falls into the reaction zone. The vehicle units of the World War II era had ample vibration to jar the carefully sized wood blocks through. In fact, an entire industry emerged for preparing char wood at the time. So, next section, superficial velocity, hearth load, and gasifier sizing. An important factor used in choosing dimensions of any gasifier is the superficial velocity, or V sub S, of the gas calculated where it passes through the narrowest part of the gasification zone. Although the units of V sub S are length over time, one should think of the superficial velocity as the gas produced expressed in terms of gas volume cross-sectional area time, a specific gas production rate. It is called the superficial velocity since actual velocities will be 3 to 6 times higher due to the presence of charcoal and the high temperature existing at the throat. A closely related term is the maximum hearth load, B sub H, expressed in volume over hearth area to H expressed in practical units. This term enables one to compare the performance of a wide variety of gasifiers on a common basis. The maximum specific hearth loads for a number of gasifiers are shown in Table 5.1. The table was calculated from the data available on gasifiers that have been thoroughly tested and lists maximum superficial velocity and heating load reported. Note that in European literature, hearth load is reported in gas volume units. In the United States, it's reported in energy units. In generator gas, GenGas 1950, a maximum hearth load, B sub H max, value for the Amber style gasifier is about 0.9 nanocubic meters over hearth centimeters squared. In other words, 0.9 meters squared of gas is produced for each square centimeter of cross-sectional area at the constriction. This corresponds to a superficial gas velocity of 2.5 meters per second, calculated at the NTP, which refers to the European practice of correcting gas volume measurements to a normal temperature and presence of 0 degrees centigrade at 1 atmosphere. In the United States, it's converted to a correct measured volume to STP, standard temperature and pressure, 77 degrees Fahrenheit, 1 atmosphere. So at NTP from the throat diameter and ignored the presence of fuel. This corresponds to a specific gas production rate of 9,000 meters squared of gas per square meter of cross-sectional area per hour. If the gas has typical energy content, this results in a specific energy rate of 54.8 gigajoules per square meter. The diameter of the pyrolysis unit at the nozzle is typically about twice that at the throat, and Table 5.1 shows hearth load in this basis also. This puts the hearth load for the Amber type gasifier on a comparable basis to the stratified downdraft gasifier. Knowledge of maximum hearth load permits one to calculate the size of the hearth needed for various engine or burner sizes. Dimensions for a variety of Amber type gasifiers are shown in Table 5.2 and 5.3. Maximum hearth load is limited by many factors, such as the mechanical integrity of the char bed structure within the gasifier, degree of agitation, and the time available for conversion. High velocities can disturb the char and fuel bed, causing instability. If char fragments become dislodged and airborne, they may plug the bed or form channels. Therefore, little agitation can effectively increase the maximum specific hearth load. The heating value of producer gas varies with flow rate, as shown in Figure 7.20. Notice that the maximum efficiency for rice hulls occurs at twice the flow rate that produces the maximum heating value from rice hulls. The maximum efficiency for rice hulls occurs at twice the flow rate that produces the maximum heating value from rice hulls. This occurs because the combination of lower temperature and low flow rates favor the methane and tar production. Although the change in efficiency is small, the benefit of reducing the tar production is substantial. Closely related to hearth areas is the cross-section area of the nozzles. Early workers observed an optimum relationship between the hearth and nozzle area. For instance, maximum power was obtained from 130 millimeter hearths that had 5 12 millimeter nozzles. Any variation of either the nozzle or the hearth rising from these dimensions caused power reduction. Table 5.2 shows successful nozzle sizes for wood-fueled Amber gasifiers and the wider variation for nozzles and used in successful Amber and SGB gasifiers. SGB units were used for two-cycle pulsating flow engines. A larger hearth diameter requires either the higher nozzle velocity or some other means to penetrate the deeper fuel bed. This leads to a higher pressure drop from large hearths, placing an upper size limit on the nozzle-fed downdraft gasifiers when gas flow is provided by engine vacuum. If the cross-sectional area of the nozzles is too small, there will be excessive pressure drop in forming the air jets. If the cross-sectional area is too large, the air jets will have too low velocity and the air will not penetrate the bed. The velocity of the air blast is shown in Figure 5.2. Turn-down ratio. Another important concept in sizing gasifiers is the turn-down ratio, the ratio of the highest practical gas generation to the ratio of the lowest practical rate. The turn-down ratio of World War II gasifiers varied between 3 for Amber-style gasifiers with insulated V hearth gasifiers and 18 for highly insulated V hearth gasifiers. Vehicle operation requires turn-down ratios of at least 8:1, making the need for insulation and proper sizing in high turn-down draft applications apparent. Although engineers often oversize equipment, this can be fatal in gasifier design. Heat losses tend to be independent of throughput, and at low loads become disproportionately high. A low specific hearth load may also cause tar formation problems. A high turn-down ratio is less important for electric generators and irrigation pumps that constantly operate at full capacity. In summary, the Ember gasifier design has survived the test of time in mass production. It is relatively inexpensive, uses simple materials for construction, is easy to fabricate, and can be operated by motorists with a minimum training. It supplies low tar gas from highly volatile fuels with a high turn-down ratio. Here's the disadvantages of the Ember design. Although the Ember gasifier has been the prototype downdraft gasifier, it has a number of disadvantages. The hearth construction seriously limits the range of biomass fuel shapes that can be successfully gasified without expensive curbing or pelletizing pretreatment. The stratified bed gasifier is currently under development at SERI and other facilities and discussed in Section 5.8 are free of constriction and promise to broaden the range of fuels that can be gasified. The Ember gasifiers require a high-grade, usually hardwood fuel, generally at least 2 centimeters along the smallest dimension, with no more than 20% moisture. During World War II, stringent specifications were maintained on fuel production, which was carried out at a number of licensed factories. The Ember design cannot be scaled up to larger sizes because the air enters at the sides and is capable of penetrating a large diameter fuel bed unless the fuel size is increased proportionally. The tar level, while low, usually 5,000 parts per million, is still high enough to require extensive scrubbing and disposal procedures. Groeneveld has studied the recycle of gases at the nozzle and developed improved understanding of tar combustion and improved mixing methods, shown in Figure 5.9, to permit scale-up. Unfortunately, there is no overall theory of operation for Ember gasifiers that would permit sizing the gasifier for fuels other than hardwood blocks. The geometry and flow of fuel and air are quite complex, making any attempts to model the gasifier very difficult tasks indeed. Some efforts to scale the Ember gasifier to larger sizes have realized a disastrous increase in tar production. However, researchers have met with more success when the fuel size has been increased with smaller gasifier size. Billets that were 8 centimeters in diameter and 15 centimeters long have operated well in large Ember-style gasifiers used for heating applications. Let's talk about the stratified downdraft gasifier. A new type of gasifier, which we have named the stratified downdraft gasifier, also called open top or topless gasifier, has been developed during the last few years through cooperative efforts among researchers at SERI, the Open University of London, the Buck Rogers Company in Kansas and Florida. It is also related to the Chinese rice hull gasifier. The stratified downdraft gasifier overcomes many of the difficulties of the Ember gasifier and may ultimately be the basis for improved gasifier designs. However, it has not been widely commercialized at this point. The reader must balance the proven reliability of the gasifiers discussed above against the promise of the stratified downdraft gasifier. Description of the downdraft gasifier for the stratified design. The stratified downdraft gasifier consists of a cylindrical vessel with the hearth on the bottom, as shown in Figure 5.10 to 5.12. During operations of the stratified downdraft gasifier, air and biomass pass uniformly downward through the 4 zones, hence the name stratified. The open top ensures uniform access of air or oxygen to the flaming pyrolysis zone, as opposed to the Ember gasifier. The uppermost layer is composed of unreacted biomass fuel, through which air enters. In the second layer, biomass reacts with the air in flaming pyrolysis. The third layer, which is made up of char from the second layer, reduces the pyrolysis gases. Inert char, which constitutes the fourth layer, normally is cooled to cause further reactions. However, since the fourth layer is available to absorb heat or oxygen if conditions change, it serves both as a buffer and as a charcoal storage zone. The temperatures and chemical compositions of each zone are shown schematically in figures 5.10. The top zone of the stratified downdraft gasifier may be adjusted to any depth during air operation and serves the same function as the fuel magazine of the in-burr gasifier. Fuel is added through the open top of the gasifier and should be replenished before the advanced pyrolysis front consumes all the available fuel. During oxygen operation, the advanced pyrolysis front moves much faster and is stabilized at the top of the second zone, so there's no first zone of fuel storage. Biomass must then be fed directly into the top of the flaming pyrolysis zone, and the second zone must be closed and insulated above, forming a burner section. As air reacts with the pyrolyzing biomass in the second zone, and most of the volatile wood oil is burned up to supply heat for the pyrolysis, as explained in Chapter 4. We have called this process flaming pyrolysis and distinguished it from the flaming combustion, which occurs at the absence of solids with excess air or oxygen. At the top of the second zone, the biomass has been converted to a charcoal, and all of the oxygen from the air has reacted. The final gas leaving the second zone contains carbon monoxide and hydrogen, as well as the carbon dioxide and H2O produced in the earlier stages of the combustion, as shown in figure 5.10. The carbon monoxide and hydrogen mixture already is sufficiently concentrated to be a combustible gas at this point. The hot gases produced in the flaming pyrolysis zone react with the charcoal in the third or char gasification zone to convert more of the carbon dioxide and H2O to carbon monoxide and hydrogen. Through the boudoir and water gas reactions, we call this process adiabatic char gasification. Adiabatic means no heat flows into or out of the section. During the reaction, sensible heat of the gas is converted into chemical energy of the fuel gas. The result is in this cooling of the gas to about 800 degrees centigrade, a temperature at which no further reaction is possible. Finally, there may be a zone of unreacted charcoal below the char gasification zone through which the gas must pass before it reaches the grate. This last zone has the disadvantage that char and ash from the char gasification zone must also pass through it to reach the grate. However, as we mentioned before, it provides a buffer or reservoir of charcoal that is available to accommodate the changes in power level, which otherwise might cause the grate to heat excessively. The stratified downdraft design has a number of advantages over the in-burr gasifier. The open top permits fuel to be fed more easily and allows easy access for instruments to measure conditions within the bed. The uniform passage of air and fuel down the gasifier keeps local temperatures from becoming too high or too low, while the average temperature is high. The cylindrical construction is easy to fabricate and permits continuous flow for otherwise troublesome fuels without causing bridging or channeling. Finally, the various strata are more accessible for measuring compositions and temperatures within the bed so that it's possible to compare modeling results with empirical observations. The stratified downdraft gasifier is both conceptually and mathematically easier to comprehend. Quantitative descriptions of mathematical models of the gas flow through the bed are thus facilitated. In principle, the gasifier can be scaled to large diameters because it operates as a plug-flow reactor, and the air and fuel are uniformly mixed. A 0.6 meter internal diameter gasifier has been operated successfully by Buck Rogers Company of Kansas. A 0.77 meter internal diameter gasifier produced 750 kilowatts of power, has been developed by Syngas Systems, and is being operated extensively on air and oxygen. We believe that these advantages, coupled with the design simplicity, may ultimately allow the stratified downdraft gasifier to supplant the in-burr and other earlier gasifiers, and that a number of design variations will grow from the basic stratified downdraft gasifier design here. Nevertheless, several years of experience with these gasifiers using both oxygen and air have uncovered questions that must be understood and resolved in any commercial design. So the unanswered questions about the stratified downdraft gasifier. The foremost question about the stratified downdraft gasifier design concerns char and ash removal. As the charcoal reacts with the gases in the char gasification zone, it eventually reaches a very low density and breaks up into dust containing all of the ash as well as a percentage of the original carbon. This dust must be carried away partially by the gas. However, sooner or later it will begin to plug the gasifier, so it must be removed by shaking or stirring. In-bear gasifiers have a provision for shaking the grate when used to power vehicles, are largely self-purging. Yet it is desirable to gasify as much of the char as possible before its packing increases the pressure drop. Minimal char ash removal can be accomplished automatically by using pressure sensing switches that activate the removal mechanism only when pressure begins to build. It is desirable to gasify more than 95% of the biomass, leaving only 5% char ash. The ability to remove variable amounts of char with a moving grate, which adds a second design issue to the stratified downdraft gasifier. Char consumes more than twice the mass of the oxygen required for biomass pyrolysis, and thus the high char conversion increases the overall oxygen biomass ratio. If up to 10% of the biomass is removed as char ash at the grate, then the oxygen fuel ratio decreases. In turn, the temperatures of flaming combustion decrease, and the resulting gas has both a higher energy content and higher tar content. This added control of the oxygen biomass ratio has not been well defined. A third issue with the design of the stratified downdraft gasifier is the prevention of bridging and channeling. High-grade biomass fuels such as wood blocks, pellets, will flow down through the gasifier under the influence of gravity. However, other fuels such as stringy chips, sawdust, and rice hulls can form a bridge, preventing continuous flow and giving rise to very high temperatures. Unfortunately, it is desirable to use these widely available biomass residues. Bridging can be prevented by stirring, shaking, or agitating the bed, and since the temperature in the gasifiers are relatively low, it is possible to use a stainless steel central stirring arm, such as the one shown in the Buck Rogers gasifier in Figure 5.11. A fourth issue to be added to the design of the stratified downdraft gasifier is the bed stabilization. When the gasifier operates at a stable, steady state, the flaming pyrolysis zone advances into the biomass at the same rate as the char is consumed, resulting in a stationary reduction zone at a fixed level in the gasifier. However, this zone can move up in very dry fuels, consuming the fuel reservoir and emerging at the top of the gasifier. Since no more fuel is available, the gasifier will operate in this top stabilized mode, but there is a substantial heat loss through the open top. This results in lower conversion energy and could create a fire hazard. The SERI and SGI gasifiers operate regularly in this top stabilized mode with oxygen, but have closed refractory tops and pressure feeding apparatus. Fuel must be added at a steady rate to prevent alternative pyrolysis and char gasification operations, which can generate high tar levels. We have observed higher tar levels from this pulsating pyrolysis process when using oxygen than when using air. Very wet fuels inhibit the flaming pyrolysis zone from advancing fast enough to keep up with the incoming fuel, and the zone subsequently moves toward the grate, consuming the dead char zone at the bottom. The zone may become grate stabilized at this point, or it may continue to move the grate and be extinguished. Thus, control of the reaction zone position is very important in the stratified downdraft gasifier. A number of mechanisms seem to be effective in stabilizing this position, as they are discussed in the recent paper. In summary, both understanding and commercialization of the stratified downdraft gasifier have made remarkable progress in only a few years of work, but a great deal of effort still is in progress. It is not clear whether this design ultimately will displace conventional in-bear and other gasifiers. Modeling the stratified downdraft gasifier, a mathematical model has been developed at SERI to predict the behavior and dimensions of the stratified downdraft gasifier. The model is based upon predicting the length of both the flaming pyrolysis and the char reaction zone from the properties of the biomass fuels at the gasifier as throughput. The zone lengths predicted for various sizes of biomass fuels are given in Table 5.4, and a diagram of the gasifier dimensions for the dry wood chips is shown in Figures 5.13. The predicted pyrolysis and char bed temperatures and chemical composition measured in the char bed are shown in Figures 5.14. The interested reader is referred to the papers for further details, which are beyond the scope of this handbook. Next time, we'll talk about tar cracking gasifiers. All right. Thank you so much for listening. Talk to you later.